Hi all, welcome back to 3 Deviations. In today's video, we want to talk about iterated integrals. Now, we probably don't know what iterated integrals are right now, but that's okay, we're gonna learn together. Now, iterated integrals is a super important topic, and it's how we can actually evaluate double integrals, and how we can evaluate triple integrals and quadruple integrals. However many integrals you want, you can always evaluate them through iterated integrals. And it's very easy. So you're actually going to find that when we're dealing with integration in multivariable calculus, the trouble is not going to be dealing with the actual integral of f of x, y, z, all the way however many you have, dx, and then however many you have equals the antiderivative. That's not a problem for us. We know how to integrate functions. That's easy. The hard part for multivariable calculus is going to be determining the boundaries, because we're going to be given all these shapes we need to integrate over. And they're not always going to be rectangles. Right now we're dealing with rectangles, but sometimes they're going to be like circles, or they're going to be blobs, or they're going to be areas between curves, and we need to integrate a surface over that region. And the real tricky part is going to be determining what coordinate system do we use to integrate, and what sort of bounds I will need. So that's basically a preview of the unit that we're about to cover, but it's important that we discuss iterated integrals first, because that just makes sure that we know what we're doing before we go any farther. Now, iterated integrals is based on the idea of partial integration. Now, partial integration is the idea that you can integrate a function of multiple variables with respect to one variable, holding the other variables constant. So it's very similar to partial differentiation. So what do I mean by this? So let's say I have a region which is defined as the Cartesian product of A, B with C and D. Then I can take the integral, going once along the y values, or the y interval, and once going along the x interval, and that sweeps out the area that I would like. And I can take the first integral from a to b, and then take the second integral from c to d of my function f of x and y dx, and then this is going to be with respect to dy and then with respect to dx. So that's our double integral. We can rewrite this as the integral from a to b of the integral from c to d of f of x, y with respect to y, then with respect to x. So what does this mean? So this means that I can perform a single variable integral with respect to a function of x and y. So if I'm integrating with respect to y, then if it's a function of x and y, x is held constant when I perform the single variable integration. Then inside of these parentheses, I apply the fundamental theorem of calculus independently. And then what I should be left with is an integral with respect to x of a function of only x, because since the integral is definite, everything with a y in it should be transformed into one of the bounds when we use the fundamental theorem of calculus. We can likewise switch the bounds too. We can do it with respect to x and then y as well. And that's a result. We're going to determine that the results are equivalent, and that's something called Fubini's theorem, which we'll cover in the next video. But anyways, that's the idea of partial integration. Why don't we do an example? Because this is a pretty tricky topic to understand first. But just to generalize, if I have an integral from a to b, or a1 to b1, and then I have tons of other integrals, and then I have another integral from an to bn of f of x1 to xn dx1 to dxn. The idea is similar. I can do the same thing for the two-variable case. So let's try an example real quick. So let's evaluate the integral. We're just going to evaluate the integral. Our bounds are given. We don't need to worry about that. So we take the integral between 0 and 3, then the integral between 1 and 2 of x squared y dy dx. Okay, so what do we do first? The first job is to take this first integral. So we need to find the antiderivative. We need to find the antiderivative of x squared y. dx. Now, what is this going to be? Well, y is going to be treated as a constant, so we could move with y outside of the integral. So what we get is we get 1/2. We're integrating with respect to y. So x squared is treated as a constant. So we get 1/2 x squared y squared, right? So that's just your single variable integral. And now we need to apply the fundamental theorem of calculus inside of an integral between 0 and 3 with respect to x. So we apply the fundamental theorem of calculus. We get the integral between 0 and 3 of 1/2 x squared y squared evaluated between 1 and 2 with respect to x. So what we get is we get the integral between 0 and 3 of 2x squared minus 1/2 x squared dx. Now notice what happens. I no longer have any y's in my integrand, and that's very important because that means that our iterated integral has worked. Iterated integrals only work when you get rid of the variable that you have integrated beforehand. So if there was a y there now, then that would be a problem because then our volume would have a y in it. Now what we'll do is we'll integrate this with respect to x because this is now just a single variable integral. So we can simplify. We get integral between 0 and 3 of 3/2 x squared dx, which is equal to 1/2 x cubed, evaluated between 0 and 3, which is equal to 27/2. Okay, so it's a little bit convoluted. I may have confused you a little bit, but I'm hoping that the example cleared things up. In the next video, we're going to talk about Fubini's theorem, and we're also going to talk about separation of functions and how we can use that as a product. So we'll discuss that in the next video. So we're still going to be focusing on rectangular regions just because we need to get acquainted with that. But the next topic will be double integrals over general regions, which will make things a little bit more complicated. So we'll see you then. Thanks for watching.